Welcome you again once. And now today we will continue some examples of a complete metric space, or we will see some examples of non-complete metric space. Okay. Previous we have already seen that for example here we have seen that a CAB is a complete metric space with respect to this metric, but it is not complete with respect to the integral metric. Now, today we will see that the set of all rational numbers with the usual metric of absolute value is not complete. Okay. So, let us verify this fact that the set of rational numbers is not complete with respect to the usual metric. Usual metric means dxy is equal to mod of x minus y. So, let x is equal to q be the set of all rational numbers, and the usual metric on q is dxy is equal to mod of x minus y for all xy in x. And then we will have to prove that, we will have to show that this q with respect to this metric is not complete. That is to say, we will have to produce a Cauchy sequence which is not convergent in q. Okay. So, choose a sequence xn represented in the decimal system. That is such that xn is equal to 1.a1, a2, an. Okay. An is the largest rational number satisfying xn square is less than 2, strictly less than 2. Then we have the sequence of numbers of this type. X1 is equal to 1.4, x2 is equal to 1.41, x3 is equal to 1.414, x4 is equal to 1.4142, x5 is equal to 1.41421, and so on. Okay. And this way you can see that after, as I mentioned earlier, if suppose we will consider how we will prove that this sequence is a Cauchy sequence. So, for every epsilon positive, there exists a positive integer capital N. Okay. So, let us take, if suppose we are considering these two terms, okay, if we are considering for every epsilon. So, if we are choosing epsilon is equal to 0.0003, okay, then we will see that there exists a positive integer n4. Okay. So, after n4 you will see the difference of x1, x2, x4 is less than epsilon. Similarly, so according to the epsilon, we can find a positive integer n such that the distance between any two elements of the sequence after that natural number is less than epsilon. So, now that you can see here is because dxm xn, let us suppose n is greater than m. So, n is greater than m, then we can write by the definition of the usual metric, this is equal to mod of xn minus xm. And but this is what? The xn and n is greater than m. So, up to m, if you take the difference, because this is the terms of this, so up to m, all the 0.0000, they are all 0. But then you will have x a m plus 1 and it go up to a n. Okay. But this term is less than, this term is less than 1 over 10 raised to the power m, because here is, this is the mth. Okay. So this is 1 over 10 raised to the power m. So, if you take m for m, so for each epsilon, okay, so if we are choosing epsilon is equal to 1 raised to the power 10 1 over 10 raised to the power m, then there exists a positive integer, that is your capital N, which is equal to m. Okay, such that this is less than 1 over 10 raised to the power m for all n is greater than m, and n and m are greater than or equal to capital N. Okay, and therefore you can see that this converges to 0 as mn tends to infinity, and therefore dxn is a Cauchy sequence in the set of all rational numbers. But we know that this sequence converges to square root of 2, but square root of 2 is not an element of Q, and therefore xn is a sequence in Q which does not converge to a point in Q, and therefore Q is not complete. So this way we can say that the set of all rational numbers with the usual metric is not a complete metric space. Take another example which is not complete. So we are considering x is equal to open interval 0, close interval 1 with the usual metric, and then this space is not complete. Why it is not complete? We can see that if we are considering a sequence xn is equal to 1 over n, okay, and then we can see very easily that dxn xm is equal to mod of 1 over n minus 1 over m, okay, which is less than epsilon for all n is greater than m. So for every epsilon you can find a positive integer n, such that you can prove that this sequence is a Cauchy sequence. And that you can also see that if you consider a positive integer n, you can take the positive integer n according to your choice as epsilon, and you will see the difference between for example 1 over 1000 minus 1 over 1001 is very, very small. Okay, so the sequence is a Cauchy sequence, and we know that this sequence converges to 0, but 0 is not in this set, and therefore the sequence, so this x is not a complete metric space. Okay, check whether Rn with respect to the matrices which we have considered in our earlier talks. There we have defined several kind of the matrices: usual matrices, LP, DP matrices, D infinity matrix, D1 matrix, or taxi cab matrix. So whether Rn is a complete metric space with respect to these matrices or not. Here is the very important thing is that we can see that okay, in general, if you have any real number x1, x2, xn, then the summation k runs from 1 to n xk square whole raised to the power 1 over k is less than or equal to summation I runs from 1 to n mod of xk, which is less than or equal to n times maximum of k runs from maximum is taken over k runs from 1 to n mod of xk, which is less than n times summation I runs from 1 to n xk square whole raised to the power half. Now you see that this okay, indeed the first inequality follows on squaring both the sides. So if you square both the sides, so this is the square, so what you will get? You will get, for example, here you say if you have two elements, then x square plus y square, okay, and on the right hand side you will have x plus y whole square. So of course x plus y whole square is always greater than x square plus y square, and you can extend this for your n terms. So this is less than or equal to this one. Okay, and now the summation of the x1, x2, the summation of mod of x1 plus mod of x2 plus mod of xn. Okay, so whatever is your, if you take the maximum of mod of x1, mod of x2, mod of x3, and number of terms are n, so this must be less than or equal to n times maximum of mod of xk. Okay, And the third term is a consequence of this factor. That is to say, mod of xk is always less than or equal to the summation I runs from 1 to n xk square whole raised to the power half. So this inequality holds good for the real numbers x1, x2, xn. Now with this real number, we can say that all these three things. Okay, now let me tell you one thing more important. You can prove these three, the Rn with these three matrices is a complete metric space. How can you do? You can do by using, as we have proved that Rn is a complete metric space with respect to the usual metric. In the same way as we have proved that this is Rn is a complete metric space with respect to the usual metric. Okay. In the same way, we consider a sequence xn of element of Rn, and then you use the same technique as we have done previously for Rn with the usual metric. The other way is that we can use this inequality. If we use this inequality, okay, and we will see that this is what, if we say, look here is, if we write here is, we can write, we can replace xk by xk minus yk whole square. Here is, we can write mod of xk by, replace this mod of xk minus yk, and here we replace xk by xk minus yk whole square. And then this would be your usual metric. Okay, and we know that with respect to the usual metric, Rn is a complete metric space. So it would be complete with respect to this metric as well as with respect to this metric. So this we can see that, look here is, so this let xy be two element, and then by using the previous inequality, that is to say this inequality, we can write in this way. We can replace xk by xk minus yk, and here is again xk minus yk, and here is xk minus yk, here is also xk minus yk. Okay, so from this inequality, we observe that a sequence in Rn is a Cauchy sequence, or a sequence is convergent with respect to the one of these matrices, if and only if it is Cauchy or convergent with respect to the other metric. Okay, how it is? If the sequence with respect to the usual metric, okay, with respect to this, the sequence here is this is your, with respect to the, this will converge to 0. So all this will converge to 0. So if this will converge to 0, this will also converge to 0. This will converge to 0, so this also converge to 0. So we will see that if a sequence is convergent, or if a sequence is Cauchy with respect to this metric, then it is a convergent sequence or a Cauchy sequence with respect to all the other matrices. Okay, so since Rn is complete with respect to this metric, okay, with respect to the usual metric, and therefore it is also complete with respect to the other matrices, or with respect to the D infinity matrix or D1 matrix or D2 matrices. This matrix, or this is your usual matrix. So we can write in this way. Okay, so now we prove the second exercise. Second exercise is the following. Prove that the closed interval 0, open interval 1 as a subspace of the discrete metric space R is complete. Okay. Now why it is so? Because we have seen that in a discrete metric space, a sequence, a Cauchy sequence must be an eventual sequence. Okay, and therefore every Cauchy sequence is convergent. So basically, you in a discrete metric space, you will find a sequence must be eventually. So every sequence is Cauchy as well as convergent, and therefore every sequence In the discrete metric space, every Cauchy sequence in the discrete metric space is convergent, and so this is your complete metric space. But keep in mind, this space is not complete with respect to the usual metric. Try to find out a sequence which is a Cauchy sequence but not a convergent, as you have seen earlier. Okay, you can try. You try to find out. Okay, let's take another exercise where we prove that the space of all natural numbers n, with the metric dxy is equal to 1 over x minus 1 over y. Okay, so here we have the metric of this form is not complete. So the set of all natural numbers and with this metric dxy is equal to mod of 1 over x minus 1 over y is not complete. Okay. So let us prove this one. So let n is greater than or equal to 1. This n is a sequence of natural numbers. And let epsilon greater than 0 and capital N be the largest integer greater than 1 over epsilon. And if mn are greater than capital N, then we can write dmn is equal to, by the definition, 1 over m minus 1 over n. But 1 over m minus 1 over n mod, it always less than or equal to the maximum of 1 over m minus 1 over n. Okay, and this maximum, okay, because mn greater than capital N, so though this maximum of this must be less than 1 over n. But from here we are choosing n is least greater than 1 over n. So 1 over n is less than epsilon. So it means that for all mn greater than capital N, dmn is less than epsilon. It means what? It means that the sequence n is a Cauchy sequence. Now let us see whether this Cauchy sequence is convergent with respect to this metric or not. So suppose contrary that the sequence n converges to some point p some point p in a natural number, in a set of natural number, or converges to some natural number p. Let n1 be any integer greater than 2p. Okay, we are taking n1 is any number greater than 2p. Then we can take then n is greater than n1 implies, or we can say that for all n is greater than n1 we have dpn. dpn by the definition is 1 over p minus 1 over n. Okay, so this because here is we are taking so it is equal to 1 over p, because here is 1 over n is less than or equal to 1 over n1. So this is greater than or equal to 1 over p minus 1 over n1. But here is n1 is any integer greater than 2p, and therefore 1 over p minus 1 over n1 is greater than 1 over p minus 1 over 2p. And so this is equal to 1 over 2p. It means that, and p is any integer. So dpn does not converge to 0 as n or anything and n tends to infinity. So it means that for any capital N, small n greater than capital N1, this is equal to 1 over 2p, which does not converge to 0. Okay, this means that the sequence n, okay, the sequence n cannot converge to the point p, which is contradiction to our supposition that n converges to a point p. Okay, hence this sequence is a Cauchy sequence which is not convergent in the set of all natural numbers, and hence the set of all natural numbers with the metric D is defined in this way, that is to say it is equal to mod of 1 over x minus 1 over y is not complete. So this way we can say that the set of all natural numbers with respect to this metric is not complete. Take some other exercises. So let x is equal to r, and we define another metric D from x cross x to r by dxy is equal to mod of x minus y divided by square root of 1 plus x square into square root of 1 plus y square for all xy in x. Okay, so here is first you have to prove that this D is a metric on R. So I left this for your exercise, but we will prove, I will give you the proof for the incompleteness. Okay, so we will prove that the set of all natural numbers, set of all real numbers R with respect to this metric is not complete. So what again we will try to find out a sequence, okay, a sequence of real numbers such that it is convergent, it is a Cauchy but not convergent. So consider a sequence n of natural numbers, okay, and observe that D and M, okay, it is equal to, so you put is equal to mod of x n minus m divided by 1 plus n square root and square root of 1 plus m square. Now divide the numerator and denominator by mn, and then we will have this term. And this term, of course, because this term is square root of 1 plus n square plus 1, and here this term is equal to 1 over m square plus 1. So even if m approaches to infinity, n approaches to infinity, this is equal to 1 and this is equal to 1. So whole thing is 1, but if they are not approaching to infinity, so this is 1 plus something and this 1 plus something. So it is means it is more than 1. So it is it means that this term is less than or equal to with this term. So here is you have this one, but this term is less than 1 upon n plus 1 upon m. Okay, but as n tends to infinity, this approaches to 0 and this is, so the sum approaches to 0, and therefore we can say that this sequence n of natural number is a Cauchy sequence in the metric space xd, or in the metric in the set of real numbers with the metric this. And now let us see that this sequence, Cauchy sequence, is not convergent. So to prove that the sequence is not convergent, suppose contrary that the sequence n converges to some point y in R, then we have D and P is equal to this thing by the definition of the metric mod of n minus p divided by square root of 1 plus n square into square root of 1 plus p square, which is equal to mod of 1 minus, and again you divide by here you divide by n, okay, numerator and denominator, we will get this thing. But you can see that this approaches to this number 1 upon under root 1 plus p square, because n approaches to this approaches to 0 and this approaches to 0. So you will get only 1. So you will have 1 upon square root of 1 plus p square. But 1 upon p square is not 0 as n tends to infinity. So this does not converge to 0 as n tends to infinity, and therefore the sequence n cannot converge, does not converge to the point p, and which is our contradiction, that we have assumed that the xn converges to p, and therefore we see that this sequence is a Cauchy sequence with respect to this metric, okay, but it is not convergent, and therefore the set of all real numbers with respect to this metric is not a complete metric space. Take another exercise. And in this exercise, we show that, the set a subset A of R2, where y is greater than 0. Okay, set of all points x, y in R2 such that y is strictly greater than 0. That is to say, you have the x-axis and then you have y-axis. So you take only the point where y is greater than or equal to 0. Okay, so you take this is your x-axis. So only the upper portion, not including the x-axis. Okay, so here is this y is greater than 0. So y is greater than 0. So you can take only the upper portion where y is strictly greater than 0. Okay, so this is not complete with respect to the usual metric. How you can do it? You can prove that you can consider a sequence xn, yn, which is you can define at it is equal to 0, 1 over n. Okay, 0, 1 over n. But you see that if you take this sequence converges to 0, 0. This sequence converges, and you can prove that this sequence is a Cauchy sequence, but the x and yn converges to 0, 0, but 0, 0 is not in A because y is strictly greater than 0. So this is not in A. So you will see that you can prove that this is a Cauchy sequence in A, but it converges to 0, 0, but 0, 0 is not an element of A, and therefore A is not a complete metric space with respect to the usual metric. Okay, so we stop over here and we will continue some other exercises in my next talk. Thank you very much.